Welcome pre-cal students to the homework help video, page 558, numbers 83 through 102 all. Notice on number 100, we're only going to do letter A. Let's go ahead and get started and jump right into this. Here we go. Numbers 83 through 86, the directions say to find the angle in radians. Remember, we have this formula here that we have talked about, and it is theta equals S over R. Of course, S refers to the arc length that the central angle forms, that arc length right there, and R stands for the radius. So we can do this pretty quickly. We are looking for theta. So theta equals S, the arc length, that's 6, over the radius, which is 5. And so there we go. We're going to take, let me turn back quickly one page in my solutions answer book here to make sure I don't make any little mistakes anywhere. And we get 6.5 for the answer. So you could leave it 6 over 5. So your answer is 6 over 5. And by the way, remember, anytime you use this formula, theta is always going to be in radians. Always. Okay? So remember, theta in this formula is always in radians. And so when we get out our answer for theta, theta equals 6 over 5, that's radians. Okay? I'm going to write real quick here, or you could also put 1 1/5 radians, or you could put 1.2. Okay, moving on to number 84. Here's our formula: theta equals S over R. Our arc is 29, our radius is 10, and so theta equals 29 over 10 radians, or you could say 2 9/10 radians, or you could say 2.9. Any of those answers are acceptable as long as you remember they are in radians. Number 85, theta equals S over R. So in order to find this central angle right here, we're going to use our arc, which is 32, over our radius, which is 7. So theta equals 32/7 radians, or it equals 4 4/7 radians, or it equals 4 point, and I'm not sure what that would be. Let me grab my calculator real quick. It would be 4 point, that can't be right. Let's see. I guess so, 4.5714 approximately. Okay, any of those answers are acceptable. Number 86, theta equals S over R. So theta would equal arc length S, which is 60, over radius 75, and so theta could equal the following. First of all, if you reduce 60 over 75, you will get 4/5. Or you can write it as a decimal if you would like, which would be 0.8. So 4/5 radians or 0.8 radians. Okay, moving on to numbers 87 through 90. The directions read, find the radian measure of the central angle. So now we're looking for the central angle. Let's start off with number 27 first. We have a radius that's 27 and an arc length that's 6. Okay, so our formula is theta equals S over R. Notice they've given to us, I'm sorry, I didn't even realize it's going to be the exact same thing. So here we go. Theta equals arc length 6 over radius 27. And so your answer would be 6/27 radians, or 6 divided by 27, which is 0.2, repeating for the radians. Okay, and 6/27 can be reduced by 3, of course, so 2/9 radians, or 0.2 repeating radians. Let's take a look at number 88 here. Again, it's going to be the exact same formula, so I have no idea why I just erased it. Theta equals S over R, and so theta would equal your arc length, which is 8, over your radius, which is 14, and if you reduce that, you will get 4/7 radians, or if you want to write it in a decimal, it would be 0.5714 radians. Moving on to number 89. We're going to find the central angle theta, so theta equals arc length, which is 25 centimeters, over 14.5 centimeters. And by the way, let me pause and say something. If this was in inches and this was in feet, you would have to make them both feet or both inches. Same thing here. If this was in centimeters and this was in meters, you would have to make them both become centimeters or both become meters. So these two units of measure do have to be the same, okay? Anyways, moving on, we have 25 over 14.5. If you want to leave that as a fraction, you would move the decimal up top, that'd make it 250, and move the decimal on the bottom, that would be 145. And then if you reduced that correctly, you would get 50 over 29. So there's one answer if you reduce this correctly, 50 over 29 radians. Or if you wanted to type that into your calculator, you would get 1.7241 radians. Okay, moving on to number 90. Let's see, let's find the central angle theta. So theta equals arc length, which is 160 kilometers or kilometers over 80, which is your radius. Of course, 160 divided by 80 is simply going to be 2. So your answer is 2 radians. Okay, 2 radians. All right, moving on now to the next section. Let me get a drink here real quick. The directions for this section state find the length of the arc on a circle of radius r intercepted by a central angle theta. So now we're looking for the arc. Okay, so here's our formula. Theta equals s over r, and we're looking for s, the intercepted arc. So let's see, theta is 100. Let's take a look at this problem here first, this one right here. Your central angle is 180 degrees for your theta. Your s, of course, stays s, and your radius would be 15. Now, I made a mistake here on purpose, and when I make a mistake on accident, I will admit to you, hey, I made a mistake, but I did this on purpose. Did you see my mistake here? I entered 180 degrees in for theta. And remember, in this formula here, theta equals s over r, your central angle here must always be in radians. So if you're given an angle in degrees, 180 degrees, that's fine, but you need to convert it over to radians. Let me say that again. Theta in this formula is always going to be in radians, always. So if you convert 180 degrees over to radians, you will get pi. So there we go. Okay, we're solving for s, so my suggestion to you is to multiply this side by 15 over 1, so these will cancel that way. But if you multiply one side by 15, you must multiply the other side by 15. So we end up with 15 pi equals, and then over here your 15s cancel, and you're left with s. And so the intercepted arc for number 91 is going to be 15 pi inches. Of course, it is in inches. That's the length of the arc. Or if you want to type this into your calculator, you should get 47.12 inches equals your arc. Okay, let's try another one here real quick. Let's try number 92. Number 92. Okay, we're dealing with a radius of 9 feet and a central angle of 60. Now, when we go to put 60 in for theta, don't forget theta has to be in radians, and we should know how to convert degrees over to radians real quick. Remember, it would be 60 over 1 times pi over 180, and if you cancel correctly, this will be a 1, this will be a 3, you'll get pi over 3. So 60 degrees is the same thing as pi over 3. So I have pi over 3 equals s over my radius, which is 9. Now, my suggestion to you is to multiply both sides by 9 so that s is all by itself. So I'm going to multiply both sides by 9. Here my 9's cancel, which is what I wanted, and that leaves me with s. Over here I have 9 pi. 9 times pi is 9 pi. And of course 1 times 3 is 3. So I have 9 pi over 3. And if you type that into your calculator, you're going to get, well, first of all, you could cancel. 3 goes into 3 once, and 3 goes into 9 3 times, so you would have 3 pi equals s. And if you wanted to type that into your calculator, I would accept 3 pi for an answer, or you could also type 3 times pi, and you would get 9.4247, so just 9.42 would be acceptable. So 9.42 what? Well, 9.42 feet. How do I know it's in feet? Because right here my radius was in feet, so my arc also has to be in feet. All right, my arc length. Okay, let's go ahead and take a look at the next one, number 93. We have 3 meters and 1 radian. Now, notice your central angle is already in radians, so we can just put a 1 here for theta. That's easy. And then my radius is 3, so I'm going to put s over 3. Well, I'm going to multiply both sides by 3. If I multiply s over 3 times 3, I'm just left with s. If I multiply 1 times 3, I'm left with 3. It's that easy. Now look at your radius. It was meters. So my my intercepted arc is 3 meters. All right, moving on to number 93. Number 94, excuse me. Let's fix our formula here. All right, number 94. We have 20 centimeters and we have pi over 4 radians. So for theta, it's already in radians. I'm going to put pi over 4. And for my radius, I'm going to put 20 centimeters, okay? Now, I'm going to multiply both sides by 20. If I multiply the right side by 20, I'm left with s. And if I multiply this side over here by 20 over 1, my 4 would cancel with my 20 5 times, and 5 times pi is 5 pi, and so s equals 5 pi, or in other words, my intercepted arc is 5 pi centimeters. Now, if you want to type that into your calculator, you're more than welcome to do that. You would get 15.71. Of course, I rounded that. 15.71 centimeters. Okay, so I hope this is making sense. This formula right here is a real handy formula. It's really neat to use. You just have to remember what each variable stands for, and also that your theta must be in radians, okay? Well, let's move on to some more difficult problems now. This next section should be a challenge for us. Okay, number 59. Now, the directions are a little confusing, so listen carefully. Find the distance between the cities. Assume that the Earth is a sphere of radius 4,000 miles and that the cities are on the same longitude. In other words, one city is due north of the other. Now, let me show you what that means, please, if you don't mind, okay? Here we go. Let's go ahead and draw a nice picture of Earth here. Mother Earth, just kidding. And we'll get this here, there, and that's not what I wanted. There we go. That's pretty good. Okay. Let's go ahead and copy this so I can take it from problem to problem. Okay, and here we go. So there's Earth, and what they're saying is this: Dallas, Texas is 32 degrees 47 minutes north. Now, I'm not worried too much about the minutes. I will be in a second. Don't misunderstand me. Right now, I'm just going to draw a line like this, and I know I'm going to rotate up approximately 32 degrees. Okay, so 32 is about right there. That looks pretty good. So there, I rotated up 32 degrees. Okay. So there's my 32 degrees approximately, and so right here on this point, I'm going to use a red point. This is going to be Dallas, Texas. Okay. Now, look what I'm going to do next. I went north because it said to go north. Now, I'm going to erase this degree for a second. I probably shouldn't have done that. Let's leave it there. All right, now watch this carefully. Now I'm going to rotate up 41 degrees. So I'm going to start here. I'm going to rotate up, 32, and then about 9 more degrees. Okay? And so there. There we go. So that whole angle, let me put it in red for you to see, the whole angle from here all the way up to here is about approximately 41 degrees. And so this little point here is going to be Omaha, Nebraska. Do you see what I did there, students? I hope you do. From here to here is approximately 32 degrees. And from here to here is approximately 41. Now, when they say assume the two cities are north of each other, what they're saying is if you were standing on the surface of the Earth, they're both on the same longitude lines. This city here is going to be due north of this city here. Now, whether or not that's accurate, I don't know, but we're allowed to make that assumption because the directions say that we can. So, here's what they ask us to do. They want us to find the distance between the two cities. Look at this, is so cool. They're asking us to find the distance between these two cities, which is an arc length. They want us to find the distance between these two cities. So we're really just looking for an arc length. Are we not? Sure we are. And now all we have to do is find this little angle right here with one dot. Well, think about it. If from here to here is 41 degrees, 15 minutes, and 31 seconds, and from here to here is 32 degrees, 47 minutes, if we take 41 and subtract out the 32, we're going to be left with just this little angle right here with the green dot, the one that just disappeared. There we go, right in here. So with your calculators, you can use your calculators. We learned about a week ago how to do this. You know how to type in your calculators 41 degrees. Just type in 41 degrees, 15 minutes, 31 seconds, then hit minus, then hit 32 degrees, 47 minutes, 0 seconds, and hit enter, and your calculator will subtract this for you. And what it's going to give you should be 8 degrees. Now, it's probably going to put it into a decimal for you. I'm going to go ahead and tell you now what it's going to say. It's going to say 8.4752 degrees. So now we know this teensy tiny angle right here with that dot, cute little angle, is, draw an arrow to it, boom. So the central angle is about 8.5 degrees. So now if I know the angle, guys, and I know the radius is what? The radius is 4,000. I can find the arc length. Remember, anytime, let's erase all of this stuff here. Let's erase all of this, and let's just be left with the angle we're talking about. There, that's all we care about. Nothing else matters now. Okay, that's it. There. So we know our central angle is 8 degrees, 8.47, and we know our radius is 4,000, so we're ready to find the arc length. So here we go. Here's our formula. Our formula is theta equals S over R. Of course, degrees. 8.47 degrees real quick. To convert that to radians, of course you should know how to do. We've learned how to do that in the past. I'm not going to explain how to do that. Okay, we know how to convert degrees over to radians, and so it's going to be, I'm going to use 8.5. So 8.5 times pi divided by 180 is going to give me radians of 0.148. I'm going to use 0.15. So my radians would be 0.15. Now again, where did I get that? I converted 8.5 degrees over to 0.15 radians equals this over 4,000. And I'm going to multiply both sides by 4,000. And 4,000 times 0.15 is going to give me 600. And of course, S over 4,000 times 4,000 would just leave me with S. And of course, because 4,000 was in miles, then 600 would be miles. So there's the arc length. The distance between those two cities would be approximately 600. Now, the back of the book has 591.08 miles. We're close enough. I rounded probably where they did not round, but nonetheless, that's how you would do that. Okay, number 96. Same thing. So really, you could probably try this one. Go ahead and work on this one on your own. Here's my radius. And I'm going to go up north 37 degrees, so about right here. And we're going to put San Francisco, California there. Okay. And then I'm going to rotate up 47 degrees, so about 10 degrees more. And I'm not really too concerned if my drawing's not drawn to scale. And that's Seattle, Washington. There we go. So if I know from here to here is 37 degrees, approximately, and then from here to here is approximately 47 degrees. If I subtract these two from each other, then I will know this little bit of space, this little bitty angle right in here. Okay, so that's what we're going to do. So with my calculator, I'm going to take 47 degrees, 36 minutes, 23 seconds, minus 37 degrees, 46 minutes, and 30 seconds. And if I type that in correctly, I will come up with 9 degrees, 49 minutes, and 53 seconds. And if we convert that over to radians, and by the way, if you want that in degrees, I guess I could do it for you really super quick here. 9 degrees, 49 minutes, and 53 seconds would be 9.831. So the degrees would be 9.83 degrees. And if you convert that over to radians, you're going to get 0.1716. 0.1716 radians. So let's get out the eraser again. Only thing we care about now is this little angle here that has the intercepted arc that we're looking for. And of course, the intercepted arc we're looking for is this right here. And so the angle right here is 0.1716 radians. So I have my angle, and my radius, of course, is 4,000. So here we go. S equals, and it's not S equals, is it? Hold on one second. Theta equals S over R. So theta equals 0.1716. S over 4,000. If you multiply both sides by 4,000, you will come up with 686.4 miles equals S. Okay, so 686.4 miles. Let's try another one. Hopefully we're getting better at this. If I can figure this out here, is that pace? There we go. All right, good. Okay, so we're going to rotate up 25 degrees north. 25 degrees north, so we go up about that much. That's good enough. And there we go. And that point right there is going to be Miami, Florida, and that's the wrong color. There we go. Had the white one instead there, so we can get this Miami, Florida, and then we're going to rotate up 42 degrees. So 42 is probably about right there. Again, I'm just estimating. It doesn't matter if your drawing is to scale. And so right here, we're going to put Erie, Pennsylvania. All right. So we know. Now watch carefully. We know from here to here is approximately 25 degrees, and from here to here is approximately 42. So we're going to subtract these two so we can find out this little angle right here. Okay. So here we go. If you subtract these two, you will get 16 degrees, 21 minutes, and 19 seconds. I'm not going to convert that to degrees. You know how to do that. I am going to go ahead and convert to radians. You should know how to do that. And radians will be 0.2855. Okay? So let me get out the eraser. And the only thing we care about now is that little angle right there that has the intercepted arc that we're looking for. Okay? So 0.2855 is the radian measurement for this angle right here. So do we know our central angle? Yes, we do. Do we know the radius? Yes, we do. So we can definitely find this intercepted arc, which would be the distance between Erie and Miami. So here we go. Theta equals S over R. For theta, we'll put 0.2855. And for the radius, I'm going to put 4,000. If I multiply both sides by 40,000, I will get, by 4,000, I will get 1,141.81. So 1,000. Of course, I'm rounding, and so if you're off a little bit, don't worry about that. As long as you're reasonably close, 1,141.81. So I multiplied this side over here. I multiplied this side by 4,000 here, and that left me with S, and I multiplied this side by 4,000. It left me with this. So the distance from Miami to Erie is 1,141.81 miles. Now the next one's a little more challenging, so pay attention. Let me get a drink here real quick. In this problem here, we're not going to subtract the two angles. We're going to add them, and let me show you why. Okay, watch carefully. Okay, we start here, and we draw a horizontal radius. And the first one is 26 degrees. Oh, here's the key word. Look at that. South. None of the others have said south. If you'll go back and look. North, 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 north. Okay, so we're going to go 26 degrees south. So we're going to rotate this way about 26 degrees. That looks good. And we'll go ahead and do this. And we're going to label this point here on the surface of the Earth, Johannesburg, South Africa, and we're going to go ahead and put 26 degrees here. Of course, I'm rounding that. And now we're going to go to north 31 degrees. So we're going to rotate up about 31 degrees. That looks good enough. Again, we're just estimating, and we'll put a point right here, and this point will be Jerusalem, Israel. Okay, and so this angle right here is about 31 degrees. So think about it, students. I want to know the distance from Jerusalem down to Johannesburg, South Africa. Okay, so if I want to know this distance, then the angle I want is this whole angle right here. So I've got to take this angle here, which is this, and this angle here, which is this, and add those two together, which is exactly what I'm going to do. So with that in mind, let me go ahead and get out my handy dandy eraser and get rid of all of this stuff in the middle here. And now all that I care about is one thing, and that's finding this angle right here. So I'm going to add these two together with my calculator. If I do that correctly, I should come up with 57 degrees and 58 minutes. If you convert that over to a decimal and then convert it over to radians, you should get 1.0117. 1.0117, and that would be the radians for this angle right here. So, do I know the central angle? Yes. Do I know my radius? Yes. Then I can definitely find this intercepted arc very quickly, and I will do that right here. Theta equals S over R. Theta is 1.0117, and that would equal my intercepted arc S over my radius of 4,000. So if I multiply the right side by 4,000, I'm left with S. And if I multiply this side over here by 4,000, I am left with 4,046.8. 4,046.8 miles. And that is really cool how that works, okay? So hopefully the first one we did was probably a little confusing, then it got a little easier, then a little easier. Now the next ones, these next 2 or 3 are going to be really difficult, so please pay attention and we'll see how we do on these, okay? Here we go. Okay, a car is moving at a rate of 65 miles per hour and the diameter of its wheels is 2.5 feet. Find the number of revolutions per minute the wheels are rotating. Now, let's just stop and think about this for a second, okay? Here we go. Here's my tire. It's struggling, obviously, so we're going to fix it. Make it a little, hopefully more round. Okay, so there's my tire. And I know the diameter is 2.5 feet, so I'm going to go ahead and sketch a diameter here going across the tire. Here's my tire. Diameter is 2.5 feet. That's pretty easy. We can all understand that. Now, it's saying that I'm traveling right now at a rate of 65. Now watch this carefully. Miles per 1 hour. Now write that off to the side and leave it there. Okay, we're going to come back to that later. I'm just writing all my information down. Okay. Now, they want us to find the number of revolutions per minute. Now, students, think about it. There's no way I can find the number of revolutions per minute unless I know how much distance a revolution is. Let me show you what I mean. If this tire were to rotate like this, one whole revolution like that on the ground, so it started here. Let me do this real quick. I'm not sure if this will work. Let's try this real quick. Okay. If this tire were to rotate on the ground, well, it's supposed to move, and it's not going to happen. Okay. So pretend the tire is spinning, and as the tire is spinning, it moves across the ground like this as it spins. Think about this. Whatever the circumference is how far it's going to travel on the ground. Boy, that was important. Let me say that again. Whatever the circumference is of the tire, that's how far it's going to travel on the ground. Guys, that makes total sense. Look, if you start here and put a little piece of chalk on the tire, put a little mark, and you rotate the tire like this, so it goes all the way around. When it's done spinning around, it's going to be, the tire is going to be over here somewhere. The distance that it traveled on the ground from here to here is going to be the same thing as the circumference of the circle. Now, if you don't understand that, can you at least not write that down somewhere? 1 revolution equals the circumference. You can at least memorize it. Some of you understand that, some of you probably don't, but that is true. If this tire rotates one whole revolution, the distance it's going to travel on the ground will be the same as the circumference. So before I do anything, I really need to find the circumference of this tire so that excuse me, so that I know how far it travels on the ground. So let me get a drink here real quick. And here we go. Okay. The circumference of a circle is pi d, and the diameter is 2.5. So the circumference equals 2.5 pi. Because where d is right here, I put 2.5. Got it? So my circumference is 2.5. And what I just tell you, the circumference is the same thing as the distance of one revolution. So I can now state this somewhere. I can write down 1 revolution equals 2.5 pi. Now personally, I would like to leave it 2.5 pi for as long as possible, so I'm not rounding too early in the problem. So we're going to leave it 2.5 pi right now. Now let's come back over here to this. Right now the speed that we have is 65 miles per hour, but I want to change that to revolutions per minute, right? Okay, so no problem. First of all, I want to change miles to revolutions. Okay, so let's go ahead and get this out of the way. Hopefully you still have notes on all of this, and let's get this out of the way. All right, now watch what I do, students. Please watch this carefully and we'll be home free. Okay, now watch. I have 65 miles over 1 hour, so my goal when I'm all said and done is to end up with what over here? Revolutions up top. That's what it says. Revolutions over what? Minutes. That's my goal. So here we go. Well, look, if I want to change 65 miles over to revolutions, I better go ahead and type this in my calculator so I can really see this. So 1 revolution equals 2.5 pi, which would be this right here, 7.854 feet. Now, Mr. Earhart, how did you know it was feet? Guys, your diameter was in feet. So when you found the circumference and you took pi times the diameter, you were taking pi times 2.5 feet. So 1 revolution equals 2.5 pi feet. So 1 revolution equals 7.854 what? Feet. So students, there's no way I can get miles all the way over to what? Revolutions, unless I first convert my miles to feet, because my revolutions over here is in feet. 1 revolution is 7.854 feet. So I'm going to take my miles, 65 miles, and I'm going to multiply it by 5,280. And when I do that, I now have this many feet right here. 343,200. Okay, now let's not worry about the denominator right now. We'll fill all this in later. Don't worry about that. Okay, all right. So 65 miles is 343,200 feet. Now I want to convert this over to revolutions. So let's think about this for a second. It's really not too hard to do, students. It's not too hard to do at all. Think about it. Every 7.854 feet, you get 1 revolution. So I'm going to take my 343,200 feet, I'm going to divide it by 7.854. I'm going to hit enter, and now I have this for my revolutions. I have 43697, and I'm going to cross off this revolution. Sorry guys to be so sloppy. 43,697.48. We'll just round it there. So there, I did it. It's in revolutions. So I took my miles, I converted it to feet, I took my feet, and I converted it to revolutions. So I'm doing awesome, okay? And remember, none of this would have been possible if I first hadn't found the circumference of the circle. Because, let me get a drink here. The circumference of a circle equals 1 revolution that's going to travel on the ground. Now, look, don't lose sight of the trees for the forest. My goal for letter A was to write the speed in revolutions per minute. Well, I've got the revolutions. Now I've got to get the minutes. Okay, so 1 hour equals how many minutes? 60. So I've got 43,697.48 revolutions over 60. So I'm going to divide these two. So I'm going to type in 43,697.48 divided by 60, and I'm going to get this right here. 728 revolutions per minute. Okay? And I'm checking right now, the back of the book has 728.3, so we're right on the money, okay? So there's my revolutions per minute. Got it? Okay. Now, if not, you might want to back this up and watch it again, okay? Because you got to really make sure you understand what I did there. Now let's move on to part B. So here's the answer to part A. We're going to use part A to solve part B. Now here's part B. find the angular speed of the wheels in radians per minute. Now don't forget, we did learn a formula for this, and I don't have it in front of me, and I know I should. I think it was the speed is theta divided by time, I believe is what it was. I'm not sure. I don't think they used s. I forget what variable they used, but I'll put as for angular speed. Angular speed is theta over time. Okay, theta over time. Well, what is your angle? Well, students, think about it. How many revolutions did you do? 728. That means you started here and you went around how many times? 728. Too many times for me. I'm not going to draw, that's for sure. So you know that you went around 728 revolutions in 1 minute. Now, one revolution is how many degrees, excuse me, is how many radians. One revolution is always how many radians? 2 pi. We know that, guys. Here's a circle. Here's an angle. Let me not draw like that. I'm sorry. Here's a line. If I start here and go all the way around, that's 360 degrees or 2 pi. So I know that one revolution is 2 pi. And I know I did 728 revolutions. So for my theta, my angle, I'm going to put this. I'm going to put 728 times 2 pi. Now what is my time? Well, 1 minute. So with my calculator, I'm going to type 728 times 2 times pi, and I'm going to get this right here, 4,574.16 radians per, and that is radians, even though it looks like Greek, radians per minute. Let me check the answer key always to make sure we're not making a mistake. And they have 4,576. Of course, that's definitely close enough. Okay, let me get a drink here real quick. And there we go. Angular speed is always going to be in radians per something, radians per minute, radians per second, radians per hour, whatever it might be. Okay. All right, let's go on to number 100. This will be an interesting problem. A 2-inch diameter pulley on an electric motor that runs at 700 revolutions per minute is connected by a belt to a 4-inch diameter pulley on a saw arbor. Find the angular speed in radians per minute of each pulley. Okay, no problem. Here we go. Here's my 2-inch pulley, and here's my 4-inch pulley. Okay. Now, let's go ahead and put a diameter going across, and this one's 2 inches. And let's put a diameter here. I hope you're taking really good notes on this if you're confused. 4-inch. And of course, what it's saying is there is a belt here, and it connects here, and it circles around, and it hits here and circles around, and this thing here spins around and around, and this thing here spins around and around, and the pulley of the belt, of course, moves, etc. Okay? All right. Now, let's start with a 2-inch. Let's start with a 2-inch diameter pulley first, because it tells us the revolutions per minute. It's traveling at 1,700 revolutions per minute. So this one, students here, this one should be really easy to convert over to radians per minute. I mean, it should be really easy because you know the revolutions. You know that every revolution is how much? 2 pi. And you know the formula is theta over time. And our time is good. Look what we have. We already have minutes right here. See this? It says 1,700 revolutions per minute. And we're trying to find the angular speed in radians per minute. So we're doing great, okay? So we already got minutes down here. Did not mean to do that. And so I'm going to put 1 minute here. That's our time. And of course, our theta, our angle in radians, every revolution is 2 pi. So my angle right here, which I'm going to try to grab and pull out of here, my theta is going to be 1,700 times 2 pi, because one revolution is 2 pi and I have 1,700 revolutions. So if I take my calculator and multiply these together, I get 3,400 pi radians per minute. Now, if you want to take your calculator and type in 3,400 times pi, 3,400 times pi, I'll do that for you real quick. 3,400 times pi, you will get 10,000. Let me write this down for you. You will get 10,681.4 radians per minute. Now, I know I'm kind of sloppy, but you can write a little neater than that. Okay, so there, we did it. We took this little small pulley that had a diameter of 2 inches, and we knew from the given up here that it was traveling or turning at a speed of 1,700 revolutions in 1 minute. So we knew we could quickly change that to angular speed because, I mean, 1 revolution is 2 pi, and we have 1,700 revolutions. So 1,700 times 2 pi, and we have our angular speed. Now next, they want us to find the angular speed of this pulley here. Now, you know what we're missing, students, over here for this pulley? I wish we knew the revolutions per minute. And I would love to be in class there with my students and see if some of you could figure this out, because it's really not super difficult if you just stop and think about it. Okay, now if these two, please listen to me carefully, students, if these two pulleys were boulders, okay, you go like this and move it down a hill there, and they're rolling down a hill, okay, they're rolling down a hill like this. In order for these two boulders to keep the same distance apart, they must go the same what? Speed. Doesn't that make sense? It does to me. It makes total sense to me. But just because they're going the same speed doesn't mean their revolutions will be the same. In fact, if you think about it, in order for this little ball, this little boulder to go as fast as this big boulder, this one's going to have to turn faster. It's little. It's got a little diameter. It's got a little circumference. So in order for it to cover a certain amount of distance on the ground, it's going to have to actually revolve quicker to have the same speed as this boulder over here. Look at like two people. One more thing, one more example. Here's a big dad and here's a little kid. If they're both walking at 5 miles an hour because his legs are smaller, he's going to have to move his legs quicker. I mean, his strides are going to have to be a lot faster than this guy because he has longer strides. Now, they're both going to walk the same speed, 3-4 miles an hour, but these legs here will have to rotate, or in other words, move faster, even though they're going the same, even though the two men or the two humans are going the same speed. So it's the same concept here. I hope you're getting that. So here's what I'm trying to show you. The smaller diameter is going to have to rotate. Put 2 inches here. The smaller pulley diameter is going to have to rotate or revolve faster than this one. And this one here is going to revolve slower. Now the question is, how much slower will the revolutions be? Well, let me ask you a question. Since this pulley is bigger, its circumference is bigger, so it's going to cover twice. Now listen to me, notice this diameter is twice as big as this diameter, so the circumference here is twice as big as this circumference. Thus, when this thing makes 1 revolution, it's going to cover twice as much ground as this one. So these revolutions here, the bigger one's going to move slower because it covers more ground in 1 revolution, and because it covers twice as much ground, its revolutions are going to be divided by, cut in half. So because the diameters are cut in half, or twice as big, however you want to look at it. So if the revolutions for this pulley here was 1,700 per minute, cut 1,700 in half, the revolutions for this pulley would be 850 revolutions per minute. So now that we know the revolutions per minute, isn't it going to be really easy to convert this over to radians per minute? Oh my, sure it is, definitely. And here we go, this will be easy. We know that 1 revolution is 2 pi. And we have 850 revolutions. So I'm going to take 850 times 2 pi, okay? And then, of course, that's over 1 minute. And if you take 850 times, let's see here, if you take 850 times 2 pi, let me get my calculator out, you are going to get the correct answer, which is 5,340.7. So 5,340.7 revolutions, or excuse me, radians. That would be radians per, I'm really making this sloppy, 5,340.7 radians per minute. All right? Okay, let's move on to number 101. The radius of the magnetic disk in a 3-point-inch diskette is 1.6 inches. Find the linear speed of a point on the circumference of the disk if it is rotating at a speed of 360 revolutions per minute. So first of all, let's get a picture of our circle. Here's our magnetic disk, and it's not very good, so I think we'll try it again. Here's our circle. All right. And then the diameter, of course. Well, they tell us the radius. The radius is 1.68. So if I multiply that by 2, I'm going to get 6 carry my 1, 3 carry my 1, 3.36. So if the, is that right? 6, 3, yeah, 3.36. So if the radius is 1.68 inches, then the entire diameter all the way across will be 3.36 inches. Now, they tell us they want us to find the linear speed of a point that's on the circumference of the disk. So the point is right here, and they're saying what is the linear speed as this little point here would spin around the circle, okay? If the disk is rotating at 360 revolutions per minute. Now this really resembles our very first problem, students, right here. When we're talking, converting something from miles per hour to revolutions, or in this case over here in this problem, we're converting it from revolutions to linear speed. Of course, linear speed is miles per hour, feet per hour, whatever. You're going to have to find the circumference like we did back here. We're going to have to find the circumference because the circumference always tells you what one revolution is, and please don't forget that. So let's go ahead and find the circumference of the circle, because remember, we know this, students, the circumference of the circle equals 1 revolution, which would also be the same amount of distance traveled on the ground. So here we go. The circumference would be pi d, so 3.36, which is your diameter, times pi. So there's your 1 revolution. So we know that when this thing travels 1 revolution, it's traveled a distance of 3.36. 3.36 times 3.14. It's going to travel approximately 10.55, and don't forget it's in inches, so there's your circumference, which is 1 revolution. Now that's a big help, okay? Now we know that 1 revolution is this many inches. Okay, now here's what we have. Please watch carefully, students. Here's what we have. Okay, let's slide this out of the way here if we can. There we go. Okay, they tell us the speed of this little dot right here is 360. Now watch this. Revolutions per minutes, or per 1 minute. Now the only thing I don't like about this problem is they don't tell you how they want your linear speed written. Do they want miles per hour? Do they want inches per minute? What do they want? So I looked in the back of the book, and what they want is inches per minute. Okay, so our goal over here, when we're all said and done, is to have inches up top and minutes in the bottom. Well, the bottom's already taken care of. We have 1 minute, and of course 1 minute equals 1 minute. And now we've got to convert our revolutions to inches. Well, 1 revolution is 10.55 inches. I have 360 revolutions, so I'm going to take 360 times 10.55. All right, let me grab my calculator and do that real quick. And if you do that correctly, you're going to get 3,798 inches. Okay, so 3,798 inches per minute. All right, so that's it. This is one of the easiest ones we've done so far, not too difficult, okay? All right, this next problem is definitely the most difficult one we're going to do, and it'll take a little good amount of time, then we'll be finished for the homework assignment. Okay, students, let's take a look at number 102, our last problem. Speed of a bicycle. The radiuses, of course the plural, the right way to say that is the radii, that means plural. The two radii of the sprocket assemblies in the wheel of the bicycle of the figure are 4 inches, 2 inches, and 14 inches respectively. If the cyclist is pedaling at a rate of 1 revolution per second, find the speed of the bicycle. Now, this will be a tough problem, but hopefully if we really pay attention, we can do this, okay? So, here we go. First of all, let's go ahead and get the diameter. The diameter of this would be 8 inches. And the diameter of this smaller sprocket here, this pulley, would be 4 inches because the radius is 2. Hopefully everybody understands that. Now it says the cyclist pedals 1 revolution. So this circle here makes 1 revolution. Now remember, we've talked about this during this video in earlier problems. A bigger circle actually has fewer revolutions to go the same speed as a smaller circle. It's going to have to spin faster, okay? So notice the diameters. This diameter is 4 and this diameter is 8. Thus, that means this pulley here, this circle here is going to have to go, when it goes 1 revolution here, this one over here is going to have to make 2 revolutions because the diameter right here is twice as big as this diameter over here. In other words, look at it like this. The circumference of this circle is twice as big as the circumference here because the diameter is twice as big. So if the circumference is twice as big, that means the revolution that's going to make is twice as big. And so this one's going to be half the size, so it's going to have to spin 2 times to make up for 1 revolution over here. So when this circle travels 1 revolution, this one over here will travel 2. So what I just did is I just showed you this. Now we know that this small circle is traveling 2 revolutions. Now please listen to me carefully, students. Let me get a drink here. This circle here was not inside of this circle here. They were connected by a belt, okay? Now, this circle here, though, is inside this circle here. So we got to treat this a little differently. If you think about this, it makes total sense. When this dot here, now watch this, students, connected to this spoke right here. When this dot here on this spoke travels 2 revolutions, that means this dot here on this spoke, because they're both on a straight line, is also going to travel 2 revolutions. So when this circle here went, sorry about that, when this circle here went 1, 2, that means this dot right here also went 1, 2, because you have one circle inside of a circle. Look, it's just like this. If I have a circle like this, a circle like this, and a circle like this, and I have a rod like this, all of these points are going to make the same amount of revolutions. Okay, so when this one goes around once, this one will too, and this one will too, and this one will too, because they're all circles inside of each other. So this circle right here, okay, students, I'm back. And so, sorry, my computer just kind of crashed, so I had to stop and reload everything. Okay, anyway, so when this circle here makes 2 revolutions, this circle here will make 2 revolutions also. So here we go. When this circle makes 1 revolution, this circle makes 2, and that means the entire tire makes 2 revolutions. So here we go. The entire circle, this entire tire right here, this tire right here is making 2 revolutions in 1 minute. Got it? So our goal is to convert that all the way over to feet per second. So I want to get my revolutions to feet and my minutes to seconds, okay? So 2 revolutions per minute should be converted over to feet per second. So here we go. Remember that 1 circumference equals 1 revolution. Okay, so let's find the circumference of this circle. Remember, the diameter is 14 inches, the radius is 14 inches, so the diameter will be 28 inches. So the circumference would be pi d, so 28 times pi is going to be the circumference, and that's going to equal 1 revolution. Got it? So once again, the radius is 14, the diameter is 28, so the entire circumference of this big tire will be 28 times pi for 1 revolution. So the circumference is 28 pi, the revolution is 1 revolution is 28 pi. Now to get that into a more recognizable number, you're going to have 87.96. I'm going to go ahead and make it 88 just to make it easy. So 88 inches equals 1 revolution. Now here we go. Notice down here I have 2 revolutions in 1 minute. So if 1 revolution is 88 inches, I'm going to take 88 times 2, and that's going to give me 176 inches. So 1 revolution is 88 inches, 2 revolutions is 176 inches, and now I'm going to convert that over to feet. So I'm going to take 176 inches, and I'm going to divide that by 12, and I will get 14.7. So now what I have is 14.7 feet per every 1 second, or in other words, 14.7 feet per second. So there's the answer to letter A, 14.7 feet per second. Okay, now let's take that and convert it to miles per hour. Okay, so here we go. All right, so there's the answer to part A right here. And now part B wants us to end up with miles per hour. Okay, so let's go ahead and convert 14.7 feet over to miles. So I'm going to take 14.7 and divide it by 5,280. And here's what I'm going to get. I'm going to take 14.7 feet and divide that by 5,280, and that will give me 0.002784 miles. Okay, and now we're going to take the seconds and convert them over to hours. So if I take 1 second, now watch this, guys. Excuse me. We know that 1 second, we know that 1 minute equals 60 seconds. Okay, so if I have 1 second, then that's the same thing as 1/60th of a minute. Okay, so 1 second is 1/60th of a minute, and then we know that 1 hour has 60 minutes. So if I have this many minutes and I then divide it by 60, I would have 1/60th of a minute divided by 60 to give me hours. So I'm going to take 1 divided by 60 equals, divided by 60 equals, and we're going to get this right here for our hours. We're going to get 0.00027. Okay, so now we're just about finished. I'm with my calculator. I have 0.002784 divided by 0.00027 equals, and I'm going to get this right here, 10.31 miles per hour. I just took this number here divided by this number here. This is a really, really tough problem, and I definitely can see me giving you one of these on a test or a quiz, because this is pre-calculus class. But make sure you really understand this. If you have to watch it 2 or 3 times, then do that. But make sure you understand the concepts that we're using. For example, when the diameter is twice as big in one circle as another, then the revolutions are going to be either cut in half or doubled. When we're talking about revolutions, 1 revolution is the same thing as the circumference of a circle. Just make sure you're understanding all of these concepts, okay? I hope this homework video has been a help to you. If you have any questions, don't hesitate to call or email.